continue our work with word problems. This time, we'll be working with those that require formulas. This is very similar to the mixture problems that we saw in the last lesson. Here's what we have going on with this problem. We have $15,000 to invest. We have decided to split it between two accounts. We are not sure how it should be split up. That is what we need to find. What we do want is to have $1,432 in earnings by the end of the year. So the question is, how should we divide up the 15 grand to earn this? Now notice how my organization is similar to the mixture problems that we've already talked about. This is how I prefer to do things. It may not be how your instructor does things. First, we need to know how to define the splitting up of the 15 grand. We talked about how to do this earlier in this chapter. We let X be the first part, and then we let 15,000 minus X, or the total minus X, to represent the other part. One more comment before we start. We need to come up with the equation that allows us to solve for unknowns. The only number we have in the final box is the total earnings. Now remember, all terms within an equation must have the same meaning. Total earnings is I, or simple interest. We don't have this number in the other two boxes, but we do have a way to define this. Since interest can be found by multiplying principal times rate according to the formula, we will be able to represent the earnings of each account. We set up an equation that shows interest earned from the first account plus interest earned from the second account. Set this equal to the total interest earned over that year. We find $6,900 should be invested in the first account, and $15,000 minus this, or $8,100, should be invested in the second account. Let's move on to uniform motion problems. For this type of problem, I recommend drawing a picture and then placing the information in a table. Here is the key to solving this type of problem. First, focus on distances and write a true equation regarding the distances. Next, we'll substitute rate times time in for distance. This will allow us to get the unknown substituted into our equation and solve for it. From here, we just go on to solve for that unknown, making sure that we have answered the author's question. Let's get started on our problem. Let's try and understand the problem and again come up with a true statement regarding distances. We have a bus traveling on a level road and then on a winding road. The total distance between these two parts to this trip is 305 miles. Since we have no idea if the distance of the level part and the winding part are the same, we're going to assume they are different. Distance on the level road plus distance on the winding road equals 305. Let's get all this information organized in a table. This is probably one of few problems where I use a table. Notice how we have the formula across the top, distance equals rate times time. The formula says if you multiply a rate by a time, you get a distance. The times are given while the rates are unknown, and we are told that the bus could travel 20 miles per hour faster on the level road. So we put R in for the rate of the winding road and R plus 20 for the rate of the level road. With rate times time equaling distance, we have a way to express the distances that include the unknown. So going on to solve for R, we find that the rate on the winding road is 35 miles per hour and level road is going to be 20 more than that. Make sure you're answering the author's question and, as always, including units on your final answers. Here's another uniform motion problem. We have two trains. The slower train is traveling at 45 miles per hour. It gets a head start. The faster train leaves 1.5 hours later and will eventually catch up to the slower train. How long does it take the faster train to catch up to the slower train? How do their distances compare? Thinking about running a race where you give your buddy a head start because you're faster, the times you each spend running will be different, but the distances the two of you run will be the same. So for these two trains, again, the distances are the same. Setting up the table with rate times time equal distance across the top. We have the rates, we just need to know how to define the times. It will not matter which train gets the variable t. How about we go with t defined to be the Amtrak's time? If the freight train got an hour-and-a-half head start, it will be traveling longer by that amount of time. The freight train's time needs to be then t plus 1.5. Multiply across for the distance. The distances are the same as we've said earlier, so we set these two quantities equal to one another. Solving gives us a time for the Amtrak train. Let's go on to see what the author needs. We do have what the author needs. Let's just formally state this for your final answer. Now, hopefully, this section has been helpful. We have gone through a number of word problems throughout this chapter. It's a tough chapter. If you are struggling with any part of this chapter, the best advice is to seek some help. And again, hopefully this has been helpful. Thank you.